There's another type of problem where substitution is a convenient way to solve. Notice these. You actually have two equations that are in slope-intercept form, so you might think, oh, I'll just graph these. That'll be the easiest way to solve. Well, the thing is that this equation, look, the y-intercept is 17 and the y-intercept is negative 11. Here it's 10 and 20. You'd have to have a pretty big graph to be able to graph these. So when we have a system like this with two equations in slope-intercept form, we can actually use substitution as another option, right? Whether the numbers are too big, or maybe we just don't have a graph, or maybe we just prefer not to. We can use substitution as a strategy here. So in this case, here's my y, right? Here it is by itself. So what's equal to this y? Well, this is, right? Negative 5 minus 11 is equal to that y. Well, where else do you see a y? Well, here it is. Okay, and I want to be clear, these two y's are the same. Those are the same y. What's this y equal to? Well, this y is equal to 2x plus 17. So what's interesting is all these boxes, they're all equal, right? This y is equal to this, and this y is equal to this. And these y's, we know that y is equal to y, right? It's the same variable. So whatever value it is, it has to be the same. If it's 3, then this is 3. This is negative 10, and this is negative 10. So what we can conclude actually is if this is equal to this, and this is equal to this, and this is equal to this, right? If all of that is true, then we can actually say that these two boxes are equal, right? And so one way we can look at it is that I'm basically taking this negative 5x minus 11 and substituting it in for this y, right? I know it's equal to this y, so I can substitute it in for the other y. So here's what that leads me to. Okay, that means that these two are the same. They're equal because they're both equal to y. So now I'm going to solve this. I need all the x's on one side, right? So I have x's over here and x's over here. I'm going to cancel them off one side. Either side is okay. I like to work with positive numbers, so I see negatives over here. I'm going to see if I can get rid of them. These are both negative, so I'm going to add and keep the sign. And then I'm going to divide by 7. Okay, x equals negative divided by positive is a negative. 28 divided by 7 is 4. So x equals 4. That's my x value. Now I can plug that x value into either of these equations to get the y value. It doesn't matter which one. I'm going to just choose the first one. So this is y equals negative 5 times negative 4 minus 11. Negative 5 times negative 4 is positive 20 minus 11. 20 minus 11 is 9. So my answer is x is negative 4 and y is positive 9. Next one. Okay. Again, this y and this y are equal. They're the same letter, so they have to be the same, right? If this is a 5, that's a 5. This is a negative 10,000, this is a negative 10,000. This y is equal to this. This y is equal to this. So therefore, these two things must be equal to each other. I can take this expression and substitute in for that y, and my new equation is again, I have variables on both sides. I need to get them on one side. I see negatives over here, so I'm going to cancel. And if I don't have negatives, doesn't matter. I just choose a side and cancel the variables off the other side. You get x equals 2. Let's plug back in. Use that top one again. I get x is 2. and y is 16. It's your turn.